Hello and welcome to MATLAB programming for numerical computations. We are in week number 7. In this module, we are covering ordinary differential equations initial value problems. So far, we have looked at Euler's method and Runge-Kutta second order method, and we have solved a couple of problems using them. We have also looked at ODE 45 algorithm that MATLAB provides in order to solve ODE initial value problem. In this lecture, we are going to go further and use higher order Runge-Kutta methods. Before we do that, let us revisit RK2-Yune's method. What we are going to do today is the RK2-Yune's method that we had developed for a specific problem y dash equal to minus 2ty. We are going to modify that to a generic problem that takes my fun t comma y as an argument. So my fun t comma y basically generates this f of t comma y and passes it on to RK2-Yune's method. Let's go ahead and modify the code in order to do that. First, we will do this for the system y dash equal to minus 2ty. Then we will extend it to the PFR problem. Let's go to MATLAB and do this. Okay, so this is the RK2-Yune's method that we had written in lecture 7.2. Okay, so what we are going to do is, instead of this guy being hard coded into this, what we are going to replace it with is through using a function myFun. Okay, so let's first create a function myFun. Function myFun, dy equal to myFun t comma y, and dy equal to minus 2 multiplied by t multiplied by y. Okay, let's save this as myFun. Okay, so k1 should be replaced by myFun, okay, t comma y. Okay, right now k1 is basically going to be ti comma yi, so I'm just gonna replace that ti comma yi. Okay, so k2 is also nothing but f of t new comma y new, f of t new comma y new. The function f is obtained through, again, the same function myFun, so we will just do this. Okay, and that should complete our problem. Now what we also would want to do is, we probably do not need this additional t new comma y new over here, so I will just remove this and directly replace t new with ti plus h, and I will replace y new with yi plus hk1. Okay, and this becomes our RK2-Yune's method, which uses the function myFun. Let's save this and let's run. Okay, and it shows the overall curve, which looks exactly similar to what we had earlier. Okay, so let's also again look at max error. Max error was 0.0021, similar to what we had gotten earlier in lecture 7.2. Okay, so what we have done is we have generalized RK2-Yune's method to use function myFun. Now what we are going to do is to extend it to the PFR problem. Okay, so run PFR ODE was the code that we had used earlier in lecture 7.3 in order to run the PFR code. What I'm gonna do now is in addition to solving using ODE 45, I will solve using RK2 Yoon's method. Okay, so for doing this, what all I'm going to do, or mostly what I'm going to need is this part and this part. So let's just take this, copy and paste this over here. Okay, prior to solving using Yoon's method, we need to initialize. Initialization is, we just need to copy this part and paste it over here. Okay, so our T, capital T, is our independent variables. Y is our dependent variable. Y, in this case, Y has to be replaced with concentration C, which are the dependent variables. Okay, so those are the only changes that we need to make. Okay, what we shall do now is just run that particular code. Let's run this code and we are going to start getting errors right from over here. So let's go ahead and do that without worrying too much about errors. What we will do over here is just change this end volume to V equal to 5. Okay, and let's run this. Okay, we got an error, undefined function or variable T naught. Keep in mind that our independent variable was V or V naught. So that is what needs to be put over here. So this will go from V naught up to V end. Okay, that's our T in steps of H. So let's also say what H is going to be. So H is going to be 0.1. So N has got to be V end minus V0 excuse me, divided by H. That's our N. We have our Y equal to zeros, N plus 1 comma 1, and Y1 is the dependent variable. In this case, the dependent variable is C naught. So I will just replace this. Okay, and I will say initialization. Solving. Okay, and what I will do is plotting results, plot V sol comma C sol as blue line and T comma Y as dashed red line. Okay, and the other thing that we need to do is replace this with an appropriate function, EFR fun, EFR fun. Okay, let's clear all, close all, and run the BFR code. Okay, and as you can see, the red line, the red dashed line, lies exactly or almost exactly on top of the blue solid line. The red line is our Yoon's method solver, whereas the blue line is our ODE 45 solver. So as you can see over here, so this is the overall code that we have. Okay, using the ODE 45 solver, the code was very simple to obtain. Using RK2 Yoon's method, if you recall, this was the main code that we copy pasted from RK2 Yoon's over here. This was the main code, and in addition to that, we had to do some initialization. We had to initialize our H, we had to initialize our time, the independent variable T, we had to initialize our dependent variable Y. Okay, once we did that, we were able to solve this using RK2 Jones method. Okay. Okay, so what we have done is we revisited our RK2 Jones method and generalized it to use a general function myFun and the PFR function PFRFun. Next, we are going to extend this to RK4 method. The RK4 method is usually the most popular Runge-Kutta method. The RK3 method uses three weights W1 K1 plus W2 K2 plus W3 K3, whereas RK4 method also uses a fourth weight plus W4 K4. The RK3 method has a local truncation error of h to the power 4, whereas RK4 method has a local truncation error of h to the power 5. The best RK5 method also has an error of h to the power 5. As a result of this, we do not get a big advantage by using RK5 method instead of an RK4 method. Therefore, RK4 method is arguably the most popular RK method out there. Okay, we'll solve the first problem, y dash equal to minus 2 ty using RK4 method. The RK4 method is given over here, yi plus 1 equal to yi plus h by 6 multiplied by k1 plus 2k2 plus 2k3 plus k4, etc. etc. Okay, so let's go to MATLAB. Let's open our RK2 Jones method and save this as RK4 standard. Okay, solve ODE IVP using RK4 using standard RK4 method. The initialization parts remains the same. The problem definition remains the same. Initialization remains the same. Solving using RK4 method. Okay. K1 equal to this. K2 equal to my fun of something. K3 equal to my fun of something. K4 equal to my fun of something, and yi plus 1 equal to yi plus h by 6 multiplied by k1. Let's go here and see. K1 plus 2k2 plus 2k3 plus k4. K1 plus 2 multiplied by k2 plus 2 multiplied by k3 plus k4. Our k2 was function of ti plus h by 2, ti plus h by 2, comma, yi plus h k1 by 2, yi plus h multiplied by k1 divided by 2. Okay, I will just copy this and paste it in K3 and we will do the modification as required. K3 is ti plus h by 2 again, but yi plus h multiplied by k2 by 2. So instead of k1 by 2, we now have k2 by 2. Okay, so let's paste, and the only thing that needs to change is k1 is to be changed to k2. Okay, same thing we will paste for k4, and let's see what change needs to be done. K4 is a function of ti plus h and yi plus h k3. So let's paste it, ti plus h and not ti plus h by 2, and yi plus h multiplied by k3 and not divided by 2. So we change k1 to k3 and remove divided by 2, and this is our yi. Let's save this and let's first clear everything. And let's run our RK4 standard method. Okay, and we see the same curve. This curve looks similar to what we had earlier. Let's check on errors, or let's check on max error. The max error is 7.5 multiplied by 10 to the power minus 6. As we see, when we went to RK4 standard method, there was a significant drop in the error. With the error dropped from around 2 into 10 to the power minus 3 to 7 into 10 to the power minus 6. Okay, so for the same step size, RK4 method is significantly more accurate than RK2 method, and that is one of the reasons for the popularity of RK4 method. Okay, so with that we come to the end of this lecture. What we covered in this lecture were two things. First, we improved our RK2 code so that we are able to use a generic function myFun t, y instead of hard coding it inside the code itself. Next, we extended our RK2 units method to RK4 standard method. So with that, I come to the end of lecture 7.4. I will see you in the next lecture. Thanks and bye.